Alright, I'm recording the solution for the quiz spontaneously. So far I put two questions here. The one question is about the adjusted R-squared, and the second is about the standard error. And you need to detect the outliers, just detecting them with the two standard errors. Now, the second part is going to be to check the model, the significance of the variables at this stage, and we can see that there are three variables that are not significant at this stage. So the first thing that we're going to do is to start looking at the outliers so that we can improve the performance of the model. So what I'm going to do is I'm going to go ahead and first of all try to filter this. You don't have to do this really, but this is just easier for me. Just to try to filter it from largest to smallest. No. I want the difference. I'm sorry. I want the difference. So I'm gonna take the difference between the absolute difference. It's something I'm just gonna do right now. I just came up with it. You don't have to do it. I've done it because I'm doing it now because I want to be very precise here. So here's the difference. And now I'm going to take I'm going to do this. The idea is I would like to find out which items has the largest, all right? So the largest difference. Again, not the two standard deviation, the difference, largest to smallest, okay. All right, here we go. So we have it's within two standard errors, all right. We're gonna, this is the largest, seems to be. So I am going to suggest, if you are going to do it without doing this step, you're going to end up doing it like me. I used my eyes just to take a look at the difference between the two standard errors, which is around 8.4, and the point, as we've done in class. But right now, I just want to verify, to further verify, all right? So my verification here it sounded true, that this is the highest outlier. And I'm doing this because sometimes the outliers are in the negative, right? And now let's check. This is the second highest outlier. As you can see, I have these two already bolded. So if you haven't done this step, you're still gonna get it right like me, because I already bolded these because I've just used my eyes to check the outliers, all right? So these are the top outliers. Of course, this also, I haven't looked for more outliers, but if I wanna also identify more outliers, this also sounds to be 5, the distance between it and the two standard errors. Here's the distance is a little bit slightly getting lower, but still maybe still big, it's 4. Here's another 4, yeah. And here's another 4, so many 4s, right? So it seems like there's not a big jump here. This is where the jump, as we were talking about, the jump is slowing down, and now 3, and we might find multiple 3s. Yeah, as expected, we're trying to find multiple 3s. So there aren't much jump. And then 2, and then maybe another 2. Yeah, there isn't much jumps here. They're still in the neighborhood within each other. They're not that distant. And then 1, and maybe this is the last one, in fact, I'm not sure. Yeah, there's multiple ones here. So the ones are maybe probably, and then 0.6, these are not probably influential outliers if they are 1 or lower than 1. In any case, or even 2. So in any case, as you can see here, the biggest jumps happen here. you have the one that is 7 points away, and then another one that is 5 points away, so there's a big jump. So this is why I identified these outliers. And then there's another 1, and then many 4s. So probably I'm gonna aim at getting rid of the first outlier, which is 0.392. So let's get rid of 392. How are we gonna do that? We're gonna copy this as is, start a new file, and over here, maybe I should add the series for you so you don't get wait a minute. Okay. Let's see if getting rid of the outliers will make any difference, okay? And now we are going to get rid of which one? The first outlier was why is this shifting here? What happened here? Because I shifted this column. Okay, because I shifted the column. Okay, we can. Okay, so the first outlier that we're looking at is outlier 300. And I have a feeling only the first 2 outliers are influential, if they are influential. First outlier here, 392. Let's check if 392 is influential by any chance. This is the one. 392. 392, 491. Just want to make sure because I messed up here. What happened here? Let me see. I think I just made a little mistake here. That was all right. I'm sorry. But for you guys, I'm gonna just put the serial number here for you, so you won't face any trouble during okay. All right, here. So now we're fine. 392. We need to delete 392. All is good. So this is a 392. Get rid of it. So this is data without a 392, which is the first outlier. Okay. Now let's run the analysis again. We're gonna go to data, right? Go to analysis, to regression, go okay. Get the Y here. Get the X here. And now labels, residuals, and put the output somewhere nice here. Hit okay. Let's take a look first of all on adjusted R squared. Did it get improved or got worse? 0.70. It used to be 0.704. Same thing. So it was a very slight improvement. Let's take a look at the p-value. It's still the same dilemma here. It's still the same situation. So this situation is not due to an outlier. Yeah. If you want, we can delete further one more outlier also, and to check if this. Some of you might be like, you know what? I'm going to check another outlier. If another outlier might make any difference. 380. So let's get rid. We might thinking, you know what? I'm going to get rid of 380 as well. So I'm going to take this data and I'm going to put it here, for example, and find 380. And the 380 is before the point that we deleted, so it's okay, we don't have to renumber again. 380 is right there, right? So we're going to delete 380. I'm going to run the analysis again. You don't have to do this, but some of you might be thinking, you know what, maybe I should do this. Maybe I can get a good model. Here, go here. This is your y, right? And this is your x. The output is somewhere here. Just a slight improvement, as you can see. Not much of improvement. Adjusted R-square. So the first indication is here, the adjusted R-square. Not much of an improvement, but over here, maybe there's a slight improvement here. 0.2. It used to be 0.3. So maybe there's a slight improvement here. It's going down. So you might be thinking, okay, since it's going down, let's go ahead and check if we get rid of another outlier, which is a 388. So we go again, take this data, and see what happens when we get rid of 388. 388, by the way, we didn't, it's the same here, the same numbering. We kept the same numbering, so that's good. Don't renumber again. Because the 388 based on the previous, yeah? So 388 is here, this one. So let's get to 388 and see what happens. Still, we are still far off, but who knows, we might get. This is an example of what you're going to go through as a data scout. You really need to be patient and try all possibilities. Some of you might say, why don't you just delete them all at once? Yeah, you can do that if you want. But I am the kind of person who don't like to delete data points unnecessarily. So here, adjusted R-squared. So I am used to being patient. And not much improvement really from the previous step. But over here, an improvement. Because this one was 0.8, now it's 0.7. 0.9. Now it is 0.7. This is 0.29. It's 0.26. So there are improvements, but not as much. So now, since this is the case, I am going to delete all the outliers. All right. So I'm going to take note of all the outliers here. This point. This point. This point. Come with me. This point. These 2 points. Come with me. This point. This point. Come with me. 3, 8, 5. Okay. Come with me. Okay. So this is 1. I'm gonna keep the ones below 1. So this one is also 1. So I'm gonna highlight it. And these ones are below 1. Okay, so this is the last one. So basically, roughly, I'm gonna have to get rid of all these. So let's just get started. And I'm gonna take this data set with me. Just afraid that let's see something here. For example, we deleted 392. 2. Yes, 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 yes. I make sure that the numbers did not mess up. Okay, so let's jump to 300. Most of the outliers on the 300s. So let's go to the 300s and see what we can do. So we have, guys, 389. Let's check. Where is 389? 389 is this one. 390. 391. 386. 370. 385. 330. 73. Let's take the 73. 338. 338. So this is delete, cut, go up. All right, next, this is delete, cut, go up. This is delete, cut, go up. These are 2 deletes, and these 3 are deletes. So we're going to end up with these 2 stitched up to the rest of the data set. So let's try now, since we now realize that these outliers could be influential, we could result on improving the p-value. Let's see if we delete now all the outliers, what happens. So for those students who started by deleting all the outliers, you're still okay because we ended up doing the same thing. All right, guys? Here. And input X range. And the output, let's put it here. Let's see. Okay. The adjusted R squared is a little bit better. I can see that. Let's take a look at the p-values. The p-values improved over here. 0.1 right now. This has become significant. So it has come to benefit here. So all these 3 now are significant values. Okay? So now we have only 2 that are not significant. However, we still have some outliers below 1. I'm not sure how influential they're going to be because they are below 1. We stopped here at 370. It's up to you if you want to go again and delete these outliers. Let's check. We have 1, 2, 3, and this is 4. I'm not sure if it's worth it really. I don't think it's going to be worth it. But let's say that some of the students may have taken this approach. I'm going to delete all the outliers. So I need to respect their decisions. Respecting their decisions here, I'm going to put the outliers and check what would your answer could have been. Yeah, what your answer could have been if you have taken this route. So I'm doing all possibilities for all students already. Okay, let's see. So now let's take a look. We're gonna start with 55. Yeah. Let's see, where is 55? Somewhere here. So 55, I'm gonna delete you. Goodbye. And then I'm gonna take the data set and go up, stitch up. So 55 is done. The next one is the 132 and 133. Let's go down. Let's find 100. Let's find out 132 and 133, guys. Here we go. We are here. So we're going to cut this and we are going here. How about 384, guys? How about 384? Let's take a look at 384. Yeah? 384, 384, 384, 384. Bye-bye. So now here is the data set, guys. Here's data, here's data analysis, regression, here's okay. Here's the Y. Here's the X. And here's the output. Wow. It's not that bad. 7.2 right now. Was it 7.1? We got the last reading. The last good reading was 7.1. 9. Okay, almost 7.2. 7.24. Right, all right, let's take a look. P-value 0.2, lower than 0.5. Oh my goodness, no way. Look at this. This is the kind of situations that I feel like, oh, why aren't you as good? So, as you can see here, we still have it not below 0.5. So it is still 0.075. But this exercise is really awesome because it shows you how perseverance in cleaning data, in cleaning data can get you to some good results. Now, if you want the truth, I'm not going to ask you to do this, but as for me, what I will do again 2 times 2 standard errors here, the standard errors, for example. And I'm going to find if the data still have any outliers. So if the absolute value of this guy is less than or equal to this, if I have enough data points. Some of you probably might do this if they took some other course in regression. Here. All these. There are some outliers. And count. Oh, I don't need to count. Sorry. I have 377. So if you want to see here, this, the sum over this, we have is still 69% in within. But if you're still feeling like a perseverance, which I feel it, it's very important. I mean, you can do this. This is an outlier. The 2 standard error. This is also an outlier. Maybe we have one more only. You can sort from 1 to 0 so that you can get all the zeros all at once. Let's do that. We don't have time in the quiz, right? So we're going to put this up and we put here 2SE and then we go at 2SE. We sort like that, custom sort, and 2SE start from smallest. Yes, give me all the zeros. So now I know all the zeros. So over here, I might decide I want to get rid of all these once and for all. If you want to see if this can be improved, even though I'm not sure. Let's see, surprises may happen. So over here, I'm going to take the data set again. And it's a vicious circle, huh? Okay, so now let's get started. Wait a minute. Matete. Over here, I am going to number again. You know why? You know why? Because these are a new output. And this new output has a new numbering for the data. So this is the 107 we mean. So I'm going to delete this 107. Cut. 107, bye-bye. All right. So what's next? 130. 130 delete. Bye-bye. 257. Bye-bye. 309. Three, 3, 4. 3, 3, 5. Also. No. I'm sorry, it's a 3, 5, 5. Okay. 3, 5, 5. That takes a lot of time, huh? I'm gonna put this as a bonus maybe. 3, 6, 5. 3, 6, 7. 370. 371. 373. 374. 375. 376. 377. Done. Goodbye. So here we go. And now let's get started. Last resort to improve one variable. Let's see. Looking forward for the results. Let's see. Regression. Why? Here we go. Okay, and let's see. Adjusted our square a bit better. Then, ta-da! Success! So, look at this beauty. This guy is now significant. These are all significant. Perfect. So, do you see how the perseverance of detecting and cleaning outliers, do you see how important the job of cleaning data and preparation of the data is? Now, some of you might be thinking, let's improve this and we see if this is gonna be improved. I'm not sure, but do you want to go this path? I wonder if I want to go this path. Because of one reason. Maybe in fact. Oh man. Wait a minute, the sound. It might not be even, we might not be very happy with that. Wait a minute. You know why? Because maybe it violates the fact that these values are supposed to be within the 95. Do you see? Do you see that? Wait a minute, did I do well? I didn't do well, because here, I didn't do well. Okay, it's not violating. No, it's not violating, okay? So if it's not violating, we are good to go. This is not an outlier anymore. Okay? I'm sorry, I made a mistake. I didn't freeze this cell over here. So let's do the usual. Let's take this and try to find out all the zeros. We're going to lose a lot of data here. This is the last cleaning session. Once I don't get any improvement, I might not get any improvement. If I don't get any improvement, I'm not gonna clean the data any further. This is the after each circle. Like this circle, why did I tolerate it? Because when I cleaned it up, it gave me an improvement here. But over here, it's very far off. I doubt I'm gonna get that much improvement. But in any case, I'm gonna here take this data and copy. I'm gonna paste the data here. And remember, you need a new series here because you're doing a new cleaning circle. So where is the outliers? Here they are. So now I'm gonna go over these outliers one by one, lovelies, okay? So the first outlier is 106. Goodbye, 106. And now 128. 200. 254. This is a problem with Excel, right? This is why we like Python. Because you can do all this with one line of code. So you do it very quickly. You just tell it which one to delete. It's 305. This is where you need to listen to some music, some relaxing music, right? Let's do that, guys. I'm not kidding you. I'm starting to go nuts just doing this again and again, right? Let's see, what do I have on my library downloads? Something relaxing. All right, 341, 349. Let's see what happens, guys. Fingers crossed. Oh. Is it an improvement or not an improvement? 7.4, 7.3. Okay. Let's see, let's see. Ta-da! Do you guys see that? Do you lovely see that? This is how you clean the data so that you can prep it for your senior data scientist. So now you clean the data so that this variable, oh, wait a minute, this guy, we got this guy to be significant. We got this guy to be significant. This guy is never significant. So it is 0.3, I'm sorry guys. And it is still 0.33. Do you see when do you stop? It's still 0.34 even. It has become worse. So basically, let me just not put it in green. I'm sorry guys. The sun is hitting my eyes. So here, yes, 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 yes. And this guy is no. No, 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 no. So basically we're gonna stop here. With how many observations? 369. So this is where we stop, all right? So basically, this is where we stop. We're gonna take this data output, yeah? We put here data cleaning. And now, the output that we're gonna work with. So basically, this is where we stop. And here's our data. Let's put this in a nice series. Here we go. And this is our output. So this is where we are going to decide to now to keep this data points as is. Here we have 1, 2, 3, 4, and we're gonna get rid of this. So this is data cleaning. I cut that. I shouldn't cut that. Okay, whatever. Let me cut it so I can see that. It's okay. I don't like to cut it though. You can copy and put it back. So data cleaning for outliers. Here data cleaning for insignificant variables. So we are going to take this and put it here. And now we're going to get rid of this variable. And instead, we're going to take all these variables and start with the data analysis, regression. Start with the Y. And then start with the X's. Now we have less X's, right? Only 4. All fine and all good. So all of them are green. Do you see that? Do you see this beauty? All of them are significant. So now let's take a look at the other assumptions here of linear regression. I usually like to put absolute residuals here. I'm going to put it like that. This is a very very interesting bonus, right? Bonus question. we have 95% of the data is in within 2 standard errors. So that's good news. We're not going to delete any outliers, as you may know, because deleting more outliers is not going to improve this model. We have all of the variables being significant. There's no need to further improve it. Okay, this is less than or equal 0.05, so it's good. And all of these are less than or equal to 0.05. I meant here the p-values, yeah? So now we are gonna start with the first assumption, which is the assumption of normality of the terms. Of course, over here you have to say something like the model attempts to explain about, and you put here the percentage, so it's about how much? About 73.3% of total variance or total variance in here okay. So these are very low numbers and they are within the normality, so there is no evidence. Okay, so this is number one. Number two here is the heteroskedasticity, right? With heteroskedasticity, I'm going to just jump into the Prussian-Hagen test, all right, if you don't mind. So over here, I'm going to take the residual times itself, so it is the squared residuals here. And these squared residuals, we're going to use them as the y. So here, we're going to talk about the homoskedasticity assumption. All right, so we're going to use the Prussian-Hagen test. You have time to do the visual, but I'm just going to very quickly do the, yeah, squared residuals and x or x. Okay. So now I'm going to run another linear regression, right guys? Meta-analysis, regression, and I'm going to take y being the squared residuals this time, and take it with the label. And then the x's are the usual x's, okay? So our x's are these x's. These are our x's, and here's the output. So I don't want the output to include any residuals. We don't need the residuals for this output. And here's okay. And from here we can use the chi-square metric or statistic. And the chi-square statistic is basically the number of observations times the, what was it? I forgot. It was the r square times the number of observations, right? And then we take chi distribution RT of this, and we take the degrees of freedom to be 4. And this is, as you can see, is less than or equal to 0.05. Thus, the heteroskedasticity is present. We were not able to accept the null hypothesis. We had to reject the null hypothesis that there is no heteroskedasticity. Thus, there is heteroskedasticity. And when there is heteroskedasticity, then we have to solve the heteroskedasticity. All right? The way to solve heteroskedasticity, one of the ways, is to transform this y variable. So let's get started. This way, y variable, we could be transforming it to the natural logarithm, for example, and see if this will help improve the heteroskedasticity. I'm going to delete this. So let's data analysis. Of course, we covered this in the on-demand course. So if you're not studying, it's not my fault, all right? Here's y, and here's x. And we want the output, and we want the residuals this time, right? So let's do the output. Okay. Adjusted R-square seems to be good. P-values are all even very good, right? Yeah, they are all good. They are all less than 0.05. This is E minus, E minus, E minus. So let's check now. Be patient. Take here the absolute residuals. And now let's get started. We need to find out here the two standard errors. So here equal if this value, the absolute value, is less than or equal 2 times the standard error. And the standard error should be frozen here. Give me 1 else, give me 0. And here we go. And now we want to find sum of all this. Oh, sorry. Sum of all this. Over the observations. And we have 95% of the observations are within 2 standard errors. So we are fine. Not the observations, but the residuals. So now the first is the normality assumption of the error term. For this we're going to use the skewness and the kurtosis. So let's start with skew. And then let's do the kurtosis. Alright, they are also very low numbers. This means that there's high normality, so that we have no reason to doubt the normality assumption. Let's now go to the Homoskedasticity assumption. And we're going to use the Prussian-Pagan test, and we're going to use the squared residual for that. So for that, I'm going to take the residual itself, multiply it by itself, and this will be awesome, right? And now, guys, let's start with data, the data analysis, regression, and let's start with the y being the squared residuals, and then the x being these x's over here. I don't need the residuals, but let's put the output somewhere over here. Alright, and then let's take a look at the statistic. Here is the r squared multiplied by the number of observations, and then chi squared distribution RT takes this value, takes the aha. So now it is, as you can see, it is greater than 0.05. So now we have no reason to doubt the homo evidence that heteroskedasticity is present, because we were accepting the null hypothesis of no heteroskedasticity is present. Okay, so now this is awesome, isn't it? We're doing a very good job. Now we are going to do the last. The third assumption is the multicollinearity. Multicollinearity assumption. Sorry. With the multicollinearity assumption, oh my goodness, this will also take quite a while, because we will have to do 1, 2, 3, 4, 5, 6. 6 different linear regressions to find the VIF and make sure all of them are below 5 or below 3, in fact. So now we are going to be very patient, super very patient, and we are going to do the VIF here. So we're going to start with the VIF of, oh no, actually it's only 4. No. 1, 2, 3, 4. I'm sorry. Sometimes I do so many techniques, I mess up even the easiest one, so forgive me. So this is the first one, right? This is enough space for the outputs. All right, the second one will be, so this one is done, right? So the second one will be this, being the, yep. Now the third one, no, C. This enough space. This will be taken R, and this will be red, and this black. Lastly, the acceleration. Okay, so this guy will be taken. And over here, we're going to have acceleration and so let's get started very quickly. Data analysis, regression, y is the one in red, and the x's are the x variables are all the other x variables. I guess it was in the there, and the output is here. And then we can go like that. Okay. So the VIF is equal to 1 over 1 minus r square. I'm sorry, not adjusted r square, but r square. Here, this one. So this is a problem here with multicollinearity, because it is over, VIF is over, as you can see, 5. So this is 1 over 1 minus r square. So problem here with multicollinearity, yeah? How about over here? So data analysis, regression. Here, I'm going to take this to be the y, and the rest will be the x-axis here. And let's get the output to be somewhere nice over here. Okay, and similarly, I'm going to take the VIF to be 1 over 1 minus r square, and the VIF is very high. So this model has a problem with multicollinearity after all, even when we fixed the homoskedasticity. Yeah? Data analysis, y, as you can see, is this, and x, as you can see, is this. And then here is the output. And then again, very bad. So basically, when we have very high, I expect the same to be here also. So Okay, this is not that bad. 2.5 is less than 3. But this means that we are going to have to get rid maybe of one variable. Maybe there is a very high correlation between this variable and others. And for this purpose, we're going to go and take a look at the highest VIF, 8.2 and 8. So we are going to get rid of WT. So let's start with the data set again. This is where we ended. Yeah, here's the output, the last output, right? I call usually the last one is output. So over here, I'm going to get rid of WT based on, so this is multicollinearity violated. So now I'm going to start a new sheet, and to fix the multicollinearity, we are going to start here by getting rid of WT, right? I'm going to take this here, and I'm going to just delete WT, all right? Or I can put it on the side, so I can do that too. So here's delete, and let's start with the data analysis, regression. So here, let's make sure that we have a very good model. It doesn't have multicollinearity, and here are the variables. We need the residuals. This, okay. P-values are all right. Again, we have to do the skewness and kurtosis. Let me just take this here. Sounds to be good. Now let's take the homoskedasticity. I'm going to do the, I think we've done the homoskedasticity before, but it's not going to be any different, right? But let's just do it. I don't know why I did that, just to put it square. And now let's put the analysis. The output without the residuals for now should be somewhere here. And here's okay. And let's see. So the chi-square statistic is r squared times the number of observations. Then we do chi-square RT, distribution RT. Take this, and we take the degrees of freedom 3. And we find out that it is greater than or equal 0.05. So there's no heteroskedasticity. There's no heteroskedasticity. So now we are going to move on to the VIF. Before I move this time to the VIF, here's the third one. Is the multicollinearity assumption. Not assumptions, but one assumption is only. I'd like to do the correlation this time and see how it is. Just an idea before I begin. I'm going to correlate all these three together and see labels and have the output somewhere nice here. Just would like to see the correlation matrix. Oh, there's high correlation here. There's here. Let's see. So the next part is to find the VIF. This time I'm going to do the VIF in the same sheet. I don't want to open up so many sheets, right? So the first VIF will be the VIF for this guy here. And the second VIF will be the VIF of this guy over here instead. third VIF will be for the HP. Let's get started. 3.5. There's some trouble here. What am I doing? Oh my goodness, I'm starting to 1 minus r squared. Okay, this is very good. Sorry guys. It's a long day. Okay, so we have 4, 1, and 3. So we're gonna get rid of HP, seems to be. Unless you're gonna say, despite the troubling. No, I'm not gonna say that because I can see very high correlation here. Do you guys see that? Do you guys see the very high correlation? Where is it? It's in the same sheet. Do you see the very high correlation that we detected between HP and the circle? So let's get rid of HP. That will be the last run, hopefully. So now, bye-bye. We're gonna get rid of you. All right. And now let's get started. Data analysis, regression. Y will be this, and X will be these two. And now output will be somewhere over here. And now, I forgot to put in the residuals in the output. Sorry. Data analysis, okay. And residuals and output over here. All right, so now the adjusted R squared, as you can see. And here, p-values are not okay. So if you take a look here, we are back to square zeros or square one. So here, this is not good. So what does that tell us? That will bring me back to the very beginning over here, where I was, not maybe over here, but maybe somewhere over here. We already got rid of this. We have a multicollinearity problems. So I might not, at the end of the day, we already had to delete this, not for the insignificance per se. I think it was the first one that been dropped, right? Where's the VIF analysis here? yeah, with the VIF analysis, I already deleted, it was not significant. Okay, I already deleted that. So with the VIF, the first one was deleted was this one, which is the WT also. So at the very beginning, actually WT was significant, but for multicollinearity. So this is a very interesting example that now the course to action that I will do as a data scout is to probably use another method for getting rid of heteroskedasticity, because we use the natural logarithm, but there's other methods. So there's the square root method. So maybe with the square root method, I might not have. No. Multicollinearity has nothing to do with the variable y, right? So if you're thinking this way, please don't think this way, because variable y has nothing to do with multicollinearity between the other variables. So having this said, there's a problem with multicollinearity. So the variables themselves are no good. There's multicollinearity among them, and that is a problem. This tells us that maybe I should change my teaching, and instead of starting thinking about the homoskedasticity problem and heteroskedasticity, problem, I should be probably testing the assumption of multicollinearity. However, even if you test the assumption of multicollinearity, sometimes when you're fixing, but no, I don't think when you're fixing, I think I have to admit it out and clear that probably I should be teaching this regression by looking into multicollinearity first. And if there's problems with multicollinearity, as we have seen now with the data, then there's no need to proceed with homoskedasticity and fixing the homoskedasticity. In fact, this is a very interesting example that I am doing here with you guys spontaneously for the first time. It's a very interesting one. First of all, you can learn how perseverance and is very important in data analysis. Second, you can feel the triumph when you are fixing a problem, that wow, I fixed this, I fixed that, and I fixed this and that. But probably in the way, you maybe need to also consider multicollinearity before you invest so much time in fixing the data. It's also an example of how you could get disappointed at the very, very last step. So this is quite interesting to see. In fact, from now on, I will be just thinking about multicollinearity first. But after doing my best to improve the significance by getting rid of outliers, because sometimes because the outliers are also values that affect the arrays of the x variables. So maybe deleting some points from the x variables will help us with the correlation with the multicollinearity. So basically I will start with the outliers, and second maybe I'll start with the normality of the residuals, and then third maybe it is the multicollinearity. Then from this example I have learned a lesson. First check multicollinearity, and then homoskedasticity assumption. Interesting example. Hope you all had fun working with it and reaching up to the level that I have reached. Good luck.